In the previous session, we looked at the operation of a PLL block diagram of a simple implementation of the PLL. Today in this session, we will try to relate the small signal analysis of the PLL with respect to the full simulation of the PLL. Okay. So, now consider the previous example which we had. We have this small signal block diagram with our loop filter of S and VCO. Okay. So, now I have some plots here. I will tell you how we relate these two things. So, assume this is a small signal diagram. So, assume that the frequency of the oscillator is the same as the frequency of the input. So, at time t equal to 0, we have omega out as equal to omega in, which is omega, and this happens to be 2 pi into 45 mega radians per second. Okay. There was no frequency error, even the input phase and the output phase, they were matched. The phase error at time t equal to 0 was 0. These are all the initial conditions, okay, and we have here as V error and Vc. Vc was 0, V error was also equal to 0. So, this is like we are talking about a PLL where the input and the output frequencies are same, there is no phase error to begin with, the error voltage, the control voltage, all these values were 0. Okay. Now, in this case, we come and apply a frequency step at t equal to 0 plus, you can say. I applied a frequency step at omega in. So, I have you can say delta omega in as 5 2 pi into 5 mega radians per second. You might be worrying that why I always use 2 pi into 5, because I just want to give you an explicit number which is easy for calculation, where this is 2 pi, this converts from frequency to radians, and this is frequency. So, if you are asked the frequency in hertz, this is like 5 megahertz here. Okay. This 5 megahertz frequency error between the input and the output, or if you want to convert into radians, it is like 10 pi mega radians. Okay. So, at time t equal to 0, just after t equal to 0, we applied a frequency step of 5 megahertz or 10 pi mega radians at the input. Then what is going to happen? If we assume that this particular system operates in a linear manner, then what are we going to have? This is plus, this is minus, there was no the phase error, we know a phase error is going to be with respect to the frequency error. So, as soon as we have the frequency error at the input, you are going to get the phase error. Okay. So, you can analyze this particular thing. When I have a frequency error at the input, how is my input phase related to the input frequency? We know phi in is equal to omega in times dt. Okay. So, if I apply a frequency step, effectively I am doing this delta omega, which the frequency at the input I applied, times dt. Okay. At time instant t equal to 0. That is how the input phase will keep on increasing. Okay. As the input phase keeps on increasing, you are going to have error voltage, you are going you are going to have phase error, here you are going to have error voltage, and finally control voltage and output phase will change. So, here now I will just write the gain of each block. We know initially the phase error was 0. Okay. So, PLL was locked, the gain of the KPD is equal to here 1 over 2. When the phase error is equal to 0, we have seen what is the gain of the phase error detector. So, this is radians per volt. The loop filter which we are choosing, that particular loop filter has gain 1 over loop filter transfer function is Vc by S into V error of S here, right. This is 1 by 1 plus SRC, and VCO with respect to phi out of S, this is KVCO over S. These are the transfer functions. So, you can analyze this block in using the linear gain model. So, we will do it one by one. So, let us find out from phi in to phi out what is the gain in the closed loop. I will draw the small the loop gain model of this. So, given the PLL here which you see in this particular case, the model for this is going to be, we have seen, I am just writing in terms of gain. So, I have half plus 1 by 1 plus SRC times KVCO over S. Okay. This is phi input, this is phi output. Okay. One interesting thing here you will find out that this particular model or the small signal model is same for omega in and omega out, it does not change. So, here I will first write between phi in and phi out. Phi in and phi out, this is a simple transfer function, you see the block diagram. So, the loop gain is equal to multiplication of all these blocks. So, here I will have the small signal closed loop gain as loop gain by 1 plus loop gain, where our loop gain is equal to half times 1 plus SRC times KVCO over S. As I say that, or we also know phi out of S is equal to integral of omega out. So, you can write this as omega out by S, right, and phi in of S is omega in by S. The transfer function with respect to phi and omega. So, this gain model is same as omega out of S by omega in of S. It is interesting to realize this. Okay. This is also going to be loop gain by 1 plus loop gain. Now, if we applied a unit step in frequency, where we applied that, we said the delta omega at t equal to 0, you just gave the input frequency step. This input frequency step can be analyzed using this loop. Okay. And finally, I can calculate in both the terms. So, what we want to know from all this analysis is, if I use the small signal model right now, the final steady state, the final error which I am going to get when you apply any input, different control voltages and error voltage will change, but as time passes by, you give it enough time in a steady state when there are no more when no more voltages or phase values are changing, you have a steady, you reach a steady state. So, what will be this error value in steady state? Okay. So, what we are looking here is as time t tends to infinity, what is my error value? Okay. You can find this error value using the final value theorem, that as s tends to 0, s times phi error of s. And what is this phi error of s? Phi error is nothing, but phi error is equal to your phi in minus phi out. So, here phi error of s is equal to phi in of s minus phi out of s, which is equal to, from the transfer function which we have, phi in of s divided by 1 plus loop gain. Okay. So, we got this and we applied a frequency step here in to the system. Okay. So, I will write it correct, I write in terms of the frequency transform. So, delta omega in of t is like delta omega 0 times u of t. Okay. So, delta omega in of s is delta omega 0 by s, that is the frequency change which you applied. So, the phase change which I am adding to my system is delta omega 0 by s square. So, you applied this frequency change. Okay. So, now I want to calculate as time t tends to infinity my phase error of s. This is going to be s tends to 0 by final value theorem, s times phi in of s. What was phi in of? So, let me just write it first, divide by 1 plus loop gain. We worked out the loop gain also. Okay. So, 1 plus SRC into KVCO by S. Okay. This is going to be limit of s tends to 0, s into delta omega 0 divided by s square 1 divided by 1 plus half 1 plus SRC times KVCO over S. You substitute this, S goes off, you multiply S here, what you are going to see is that okay, this goes off, S here. So, you see this cancels out, right. When you substitute S equal to 0, what you are going to find as delta omega 0 divided by KVCO by 2. So, we applied, sorry, this is here phi error of t, right. We applied a frequency error. In response to the frequency error, the phase error changes. So, let us just calculate the error which we applied in this case was only 5 mega radians per second. So, this is 10 pi, sorry, 2 pi into 5 mega radians per second divided by KVCO was 2 pi into 100 mega radians per second per volt. Okay. And so, there is half this particular half factor has units of radians per volt. Okay. So, if you do not recall, this half is having units of volt per radian, not radian per volt. So, let me just write this here. Units I am writing for half the factor, the units are volt per radian. Okay. So, we need to keep units always in mind. So, what we have here is 2 pi into 5 divided by this value, and this will turn out to be your 10 as 0.1. Okay. And phase error by 2 pi is equal to 0.0159 value. Okay. This is the value. Now, we did all this maths, and now if I say that okay, this is the value after doing a small signal analysis, I go and simulate my PLL in the same way as we did in the previous session. Okay. You see that the phase error by 2 pi is 0.1594. Okay. This is the thing which I would like to emphasize, that in the previous example, when we had the phase error frequency error to begin with, we went through time domain analysis and we figured out what the actual error voltage will be, control voltage and so on, and you understood the different plots which we had. In this case, we adopted a different approach, and the approach was that you start with the small signal model of the PLL, you apply applied some input. Based on the input, you calculate the phase error and you try to match those phase error, okay, and frequency error, whatever the error voltages and you have, with the transient simulations. And what you find here is phi error is 0.01594. This is what we calculated, and the error voltage, if you look at, this is 0.05. It will be easy for you to recall that your V error is equal to V control, and this is equal to delta omega divided by KVCO. And the delta omega which we started with our system was 2 pi into 5 here, and this is 2 pi into 100, right, mega radians per second at the top, mega radians per second per volt at the bottom. Right. So, you get 0.05, and that is what you see here, 0.05. Okay, is this not interesting that you did time domain simulations, such complicated simulations, and you found what that voltage is, whereas when we did this small signal analysis, we found the final error voltages and currents. Okay. So, now the question which we have is that whether we should go with the time domain analysis or this small signal model is good to do all kind of analysis, right, whether we apply a phase change or frequency change, or there are any limitations. Okay. So, these are the things which we need to understand, and let me tell you, the small signal model of the PLL is a simplified model of the PLL. It does not have any limitations so far. If in this particular model I need phase error, whatever phase error I need, I will get it. Whatever voltage I need, because if as per this analysis, if we applied a larger frequency error, we would have got a larger error voltage. There is no limitation to it. Okay. But in actual model, there are limitations. Okay. And what kind of limitations? Well, to begin with, I can tell you that, just think about it, you calculated that V error is going to be equal to half of, for V in and V out amplitude as 1, half of sine of phase error. Okay. So, if this is the case, V error is like this, then you will surely know that V error is always bounded between plus and minus half. It cannot go beyond this limit. Okay. If your small signal model somehow tells you that V error is greater than half or less than minus half, that means do not take that plus half and minus more than plus half or minus half as a value and use it and say yeah PLL logs and this is the final error voltage or control voltage. No, that is not the case. There is a hard limit on the error voltage which you can have, okay, in this particular implementation. How we can overcome that we will see in the upcoming sessions. Okay. Other important thing here is you see the loop filter. This is sitting here as 1 by 1 plus SRC. Okay. If I change this loop filter, if I just in place of this loop filter 1 by 1 plus SRC, if I say it has some transfer function LF of S, okay, then you will think that the final value of the error voltage which I am going to have actually depends on the loop filter DC component, because what we substituted here, we substituted S as 0, right. So, loop filter plays a very important role in getting the final value. Okay. So, we will look at the loop filter also, and we how loop filter restricts our analysis, okay, or the final PLL output. Okay. So, thank you.